Okay, so I'm going to move on from integrals, which I was working on last time. And this time I'm going to work on differential equations. And so what's a differential equation? First, I'm going to start off with first order ordinary differential equations. Differential equations are equations that have derivatives and their functions both in them. So in this case, I have an RC circuit in this first one, and my function is y. So if I were to solve this differential equation, I'd be solving for y. But y is part of the equation. And so that's what makes it a differential equation. You have an equation that has both your variable of interest and its derivative, and they're all dependent on each other. And so you can't just directly solve for y anymore because you have both y and y dot. In the second example I have, all right, so it's an RL circuit. And so now I have I and its derivative in the same equation. So if this were an algebraic equation, I just solve for I. I can't do that anymore. And so this is a fairly common phenomenon, actually. Like most things in nature can be represented with some form of differential equation. And this is when you start getting into more complicated physics, right? Like you get to complicated differential equations, unsolvable nonlinear differential equations. You get to partial differential equations, things that are crazy. We don't really care in this class. Again, I've made this point multiple times with all of these different topics I've covered. I don't care necessarily that you understand it for the sake of this class. I care in the long run that like once you take differential equations, you'll have understood it. But it's not my job right now to be teaching you what a differential equation means, what are some good ways to solve them analytically. What I want to do, though, is show you how do you have an equation of this form and then go to solve it using MATLAB. And so I don't even have to know how to solve it by hand. I just am going to solve it using effectively basic algebraic equations and then show you how to use MATLAB functions to solve them as well. And so I'm going to start with the simplest form, which is the simplest way to solve these, which is the Euler method. And so that is, in order to use both the Euler method and MATLAB ODE solvers, you need to just only have basic algebraic skills. And so you need to be able to isolate the highest order derivatives. So in these cases, you just have a first order derivative. And so it needs to be in a form of dy dx is equal to some function of time and y. So dy dt is equal to some function of t and y. And that could be y squared plus e to the t. It doesn't matter. And then you also need to be given some sort of initial condition. Or y of 0 is equal to y naught. And so in order to solve any differential equation, you need an initial condition or a boundary condition. And the higher orders you get, the more, if you get you can have systems of differential equations, you need to have more initial conditions. But we're starting with first order equations. And so for an equation of this form, you have to have an initial condition. Y0 equals y naught. And so if you know how to solve for y dot, di dt, and h dot, which is the highest order derivatives in these equations, if you can rearrange these equations so this is by itself on the left-hand side, you're already most of the way there, to be honest. The Euler method is honestly that easy. And so what you do is you isolate the derivative, and then you start to kind of manipulate things. You say, okay, so you approximate dy dt as a slope, like we did in last week when we were looking at the forward differencing method, backward differencing method. This is basically using a forward difference method for dy dt. So y of t plus delta t, or y of the next t, it would be yi plus 1 minus y of I over delta t is equal to this function on the right that I just isolated for. And now I just say, all right, so what I'm looking for in this equation, I have y. I already know what y is. I know what delta t is because I define it. I know what t and y is for every step, right? And then I need to calculate what I have at my initial state for the next one. And so I isolate now y of t plus delta t, and I get this equation. And so my general form for the Euler equation is this last one here. Y of t of k plus 1 is equal to ytk, so y of the previous step, plus delta t times that function that I isolated. And so basically what you're doing is you're calculating the next moment in time, the next step in time, with the time you already have. So you start off with the initial time. So if you're doing the first step, you'd be looking for the next step of y is equal to your current step of y, the initial condition, plus whatever step size it is, and that's something you define. You define how far do you want to step in time, and then plus this function that you've solved for, evaluated at the current time and the current y value. Okay, so how do I actually do that? So I just explained that in very general terms. So I want to use an actual example to show you this. And so this is actually going to be a fairly complicated example, more or less. I have an RC circuit. So RC, this circuit is defined by RC dV dt. V is voltage, plus V, the voltage itself. So the derivative of voltage times RC plus the voltage itself is equal to the voltage applied. And this is just, you would just have a circuit and you come up with this equation using the circuit. This, I think you probably use like Kirchhoff's voltage law or whatever. It's been a while. And suppose that RC is 0.2 and that the capacitor has an initial voltage of 2 volts. And your applied voltage has this complicated equation here. That's why I'm saying this is a kind of complicated equation, because your V applied is equal to 10 times 2 minus e to the negative t sine of 5 pi t. So solving this analytically by hand is actually, it's not super straightforward. You have this really difficult, really complicated forcing function, and then you have to solve the equation with that forcing function. You could do it, but it would take some time. But what I'm just going to show you here is going to be universal no matter what the equation is. If you can arrange it into this form right here, you can use it. It's not always the most accurate, but it's straightforward. It works. And so what I'm going to do is I bring everything to the right-hand side here. I isolate dV dt by subtracting by V and dividing by RC, or dividing by 0.2, right? And now I'm going to use MATLAB. I'm going to use a for loop to build this V vector one step at a time, one literal time step at a time. So I'm going to start at the initial voltage, which is equal to 2. I'm going to start, that's going to be 2 plus delta t, which I'm going to have to define. I'll probably use like 0.01 or something. And then plus this function right here, plus my time 0 and my voltage 2 plugged into this complicated function right here. So let's do it. So, all right, I'm going to pull this up to the side. Actually, I have the solution right here. That doesn't matter. So I'm going to set up my initial conditions first. So my initial voltage, so V of 0, V of 1, sorry, is going to be equal to 2. So my initial at time is equal to 0. There's no 0th index, right? The first number is going to be 1. So V of 1 is equal to 2. And then that's my initial value. And then I can make a time vector. T of 1 is equal to 0, right? So that's my initial time is obviously 0. So now I can go through and actually start to solve using this equation. And so I'm going to create my step size. So I'll call it dt is going to be equal to 0.01. So that's going to be my step size. And then my end time is going to be equal to 5. Then my whole time vector, this t, so let me call this time, is going to be time of 1 dt with a spacing of dt to end time. And the reason I'm defining it this way is because that way I can go and change my initial time, and maybe I could call this t naught, t initial is going to be equal to 0, and then plug that in there for time to make it a little less complicated. But the reason I'm defining it this way is because now I can go in and I can change my whole solution just by changing maybe dt, my end time, and I just have to change one number, and it changes everything. So now I have my time vector. And so for I is equal to 1 to length time. So this is my normal way I've set up for loops, right? And I want to go through my entire time array and calculate what the voltage is. And I'm going to start at the first one to calculate the next one in time. And so the thing is that I'm going to have to, if my end time is 5, I actually want to go length of time minus 1, because remember, this equation calculates the next time step of voltage. So I'm going to get to the second to last one to calculate the last time step. That's fine. That's easy enough. I could have kept it at the normal and it would have just made it longer. But in order, I have to do this in order for it to line up with my time array. Because, like I said, I'm calculating the next time step. Because I already have V of 1. And I can just plug in this equation and I'll work backwards. So V of II plus 1, right? Because that's my V of TK plus 1. K is my index. So my next step, my next time step V is going to be equal to V of II. So in the initial path to this loop, that's my initial condition, right? So when II is equal to 1, my initial state is equal to 2. So that number will be 2. Plus delta T dt times f of. So now's where it gets a little hairy. So how do I want to define this f? I'm going to define it as fun of time of II and then V of II right now, just to keep it in the same form. So there's a couple ways I could do this. And I think the way I'm going to do is I'm just going to overall define this function right now. So what I can do, and the reason I'm going to do this is because I'm going to do this as well for other, for using like ODE functions in MATLAB, is I want to define now a function. I've talked about this before. There's something called a subfunction. So if you create a function file basically a function at the bottom of your script, you can actually use that function inside of your inside of this script only, and it doesn't get saved as its own file. So let me call this voltage or voltage. This function is going to be called voltage. And so I'm going to say dV dt is equal to voltage of TV. So if you input T and V into this equation, you're going to get output dV dt, or this F of T VK. So let's do that. Let's define this. So now I need to just apply this V that I defined right here. So dV dt is going to be equal to V applied, which I've not defined yet, so I'm going to have to define that next, minus V over 0.2. And that's why I had you rearrange it, right? Is because I wanted to use this here and in this function there. So now I have to define V applied, but I did define it in the problem. It's equal to this. So my V applied is equal to 10 times 2 minus e to the negative t times sine of 5 times pi times t. And so to make sure I'm using the same time in here and the same voltage that I used here. So all these variables have to match up. This V app should match there. But now I've created that. So I could have put all this in line here, but it's a little bit easier to use it as a function, right? So it's separated from the rest of my code. But either way, it works. I could have done it in line. I could have calculated every step. But I like to create functions. They're a little bit easier. I'm going to use this function later on as well. Like I'm going to solve it using ODE 45, a built-in MATLAB function, and for that you need to create a function file for it, or a MATLAB function, quote unquote, for it. And so now I just plug that into my Euler equation here, and now it should be done. Like I know that was a lot of steps, but realistically the lines of code, it's not that many, right? It's a pretty simple solution to solve a fairly complicated problem. And so now let me plot time V and I'm going to try to match this figure here. So fig 1 is equal to figure. Fig 1 dot color is equal to white. That's easy enough. And now I can add my labels. X label, Y label. All right, let's see if it works. There, and look, I got the same answer. Isn't that wonderful? It's always a moment of truth, right? When you hit it and you go to compare it to something you know, and it worked. So I would challenge you, maybe go through that example yourself again and see. I have the solutions up online for this problem. But so that's how you do it. You literally just put this in a for loop, and this f is just going to be whatever you rearranged your differential equation to be. And so make sure you understand this, because this concept, rearranging this differential equation so that the highest order derivative is on the left-hand side and then using it as a function in the Euler equation and other things is going to be foundational for both this and multiple weeks to come. And so with that, I'm going to end this example. So I don't have any class assignment for you with this in particular, but what I want you to do is to go through hopefully yourself and just make sure you understood what I did. I have a different way I solved it here. Instead of using a function file I just did everything in line. Both ways work. So do whatever makes sense to you, and hopefully, if you might have watched it a few times, hopefully this makes sense, because we're going to move on from here and start doing other examples.